Welcome back, Bridge students. So we've reached a point in Unit 8 where students often start to get tired. There's lots of different postulates, theorems, lots of information about proofs, lots of information about proofs using rotations, reflections, translations, this kind of thing. So what I want to do is just kind of dial it back, get out of the alphabet soup, and just look at the different methods that we have so far to prove that triangles are congruent, that they have the same size and same shape. Okay? And in doing that, we're really learning a pattern of deductive reasoning. That's the larger goal. All right. So my objective here is, it says it, objective 1, students can identify the methods of proving triangles are congruent that they already know. These are things you've already learned. And I also want you to visually identify a new pattern that I introduced at the end here. It's called the AAS, or angle-angle side pattern. All right, so I have a picture here of two triangles, ABC and DEF. And I want to go back and say that the first, most basic method is to show that the two triangles, to use a word from Euclid, from way back, they coincide with one another, that they essentially land on one another through a series of translations, reflections, and rotations. So for example, in this case, you might remember that in second term, we looked a little bit at translations and at what are called vectors. Some of you may recall that. So say let's move triangle DEF along a vector. And the vector we could denote it like this. This is a little vector symbol here. And all this says is that we're going to move it 4 left. Okay? In other words, we're going to take it and we're going to go 4 left. Yeah, just like that. And if we do that, the two triangles are going to line up like you see in this picture right here. And you might want to stop and think. You have your tools here. You have translations, you have reflections, you have rotations. What might cause this new triangle, D prime, E prime, F prime, to land on top of ABC? You might think, well, it's a reflection, and it's going to be a reflection across a line. Here, I'm kind of imagining now that we're right at the origin, right here, that this point is now at the origin. You don't quite have to do it this way, but I think this makes it easier. Okay, and here's the x-axis, here's the y-axis. And if you do a flip, if you do a reflection, the point E is going to land on point B, point F is going to land on point C. In fact, it's already on point C. And if you flip point D across, it's going to land on point A. You might recall that we can express reflections using algebraic rules. In this case, it would be xy goes to. Well, let's see, the x coordinate flips, and so it goes to negative x, y. We have a flip or a reflection across the y-axis, preceded by a translation forward to the left. And as a result, we know at just a basic level that these two triangles are congruent. They coincide with one another. They one lands on top of the other. All right, so that's not so hard. Let's go back and now look at, it's called the ASA triangle congruence. Sometimes it's called a postulate. In your book, they call it a theorem. It really doesn't matter. But the idea here is that we can prove that triangles are congruent by showing that two angles in what's called the included side of one are congruent to two angles in the included side of the other. So just real quickly, that if, say, I'll use some color here, if this angle A, we'll draw a little tick mark there, is congruent to angle D. Say we got out our protractors and measured those things. And if, well, let's make it easy, if angle C, this one here, use a slightly different colored purple, I'll use 2 tick marks, is congruent to angle F. Right, and the included side, so that would be side segment AC, different color entirely, I'll use red. And this one is congruent to DF. Then the 2 triangles are also congruent. Okay, so that's a model of ASA. Here's side angle side, very similar but a little different. In this case, let's say that these 2 angles here, C and F, those guys are congruent. But we don't know about angle A or angle D, but what we do know in this scenario is, well, we could actually count. I mean, look at these, they're in graph paper. Segment AC right here, AC is going to be 8 units long, okay? So, and segment DF is also 8 units long. And we know then that this segment is congruent to this segment. All right, and we might also look over here and we could see that, for instance, I'll go back to my black color here, that like on this original triangle here, that the distance from B down to the bottom here is 5 units. This is a right triangle. This is 2 units across. And using the Pythagorean theorem, side BC is going to be the square root of 2 squared plus 5 squared. That's going to be root 29. This side is also root 29 by the same logic using the Pythagorean theorem, which means that this side here is congruent to this side here. And we have the side angle side method of proving that the 2 triangles are congruent. Same kind of deal here. We'll toss out the Pythagorean theorem here again. We know just looking at the graph paper that this is AC is 8 units long. I'll use hot pink for AC, and DF, that's also 8 units long. We just looked and we saw that BC was root 29, EF is root 29. Those 2 are congruent. And also using the Pythagorean theorem, same way, this is still 5 down here, right guys? And this is going to be 6 across. Yeah. And so that's going to tell us what this side, how the length of this side, this hypotenuse on the right triangle I've marked out in black is. And so 5 down, that squared is 25. 6 across is 36. 25 plus 36 is 61, which can't reduce anymore. This is root 61. This is root 61. And this side is congruent to that side. And so by the side triangle congruence, postulate theorem, in some ways it doesn't matter. It depends on your system for proving these things, that the 2 triangles are congruent. Now, what I want to do here is just for a sec go back to ASA, because we have another situation that kind of that evolves really from the ASA triangle congruence. I'll call it a postulate here, okay? And it's called angle, side, or AAS. In the next video, we're going to do a quick proof on how AAS works, and also look at an application of it. But first of all, I just want you to look at the pattern. So it would look like this. If we can prove that, I'll stick with my color scheme, that if F is congruent to C, and if, for instance, B is congruent to E, put my little tick marks over here, and we have a non-included side that's congruent to the other non-included side, for instance. Well, this would be non-included. That's non-included. That those two triangles are congruent, and we're going to look at some of the logic behind that in the next video. I hope that that was a clarifying review and that you're ready to move forward.